which is by Dr. Mark Blackburn, who is a senior research scientist at Stevens, as well as a member of the SERC Research Council. On the Research Council, he provides a lot of guidance around systems engineering, management and modernization, as well as digital engineering, and he's the PI on a number of SERC tasks that have to do with digital engineering and participates on several others as well. Mark's research focuses are on methods, models, and automated tools for reasoning about complex systems. And Mark's first presentation today is on transforming systems engineering through model-based systems engineering. So I think, Nico, are you bringing Mark up? Thank you.
Yep, I think I'm there, right? Can you see my screen?
Yes.
Okay, great. All right. Yes. So my sponsors, Mr. Alan Lagaska, he's on the panel, and Dr. Jason Cook, he's actually there live, so you can actually talk to them, Jason and Lisa, later if you want. All right. So this is our normal standard disclosure about we use a bunch of tools and things of that nature. All right. So I'm going to get into this. It's like this is really one of the very first times that we've actually talked very much about anything that's been done with the Army Armament Center. And so even though we were working with them for quite a while, we just haven't been able to talk about what we've done with them so much. And so I'm going to give a little bit of background on that. Normally we actually been talking about NAVAIR and throw in a couple of slides. Basically the next talk on Space Force, so it's going to be an extension of what we actually did, probably more from a NAVAIR point of view. And so then we're also going to talk a little bit about the enabling technologies and methods that we've been developing for a number of years, and how we actually produce what we refer to as the full stack of models, from mission, system, analysis models, subsystems models, and then how we create various different kinds of simulation workflows that are coordinated through this thing called the Armament Interoperability and Integration Framework, which I'll be explaining in more detail here. And then how well have we done over the years? Well, one of the goals of SERC research is actually transitioning that research into different kinds of things that can be used by our sponsors. And so we basically have developing the second training class that I'm going to talk about a little bit of that use case right here. So in 2015, we started work with NAVAIR. We were working with NAVAIR in 2013. And so one of the problems looks in some ways like this is a very traditional kind of problems where in some ways what you want to be able to do is that you describe whatever the mission objectives are. And one of the things with NAVAIR, they were actually talking is they wanted to optimize that. A lot of times they threw in so many kinds of things that used to be, say, mission requirements, and what they did is that they wanted to right size that. So by doing so, we have done a lot more work in terms of trade space analysis at the system level and the requirement level, and also looking at it at the how it's done from various different kinds of analysis and to how well it's done. And one of the key things that we've been able to formalize is that underlying these kinds of things, there's a lot of requirements, design, and analyses that are not tied together. And so what you're going to hear is our formalization of how we've done that. And once you do that, then you can actually query the information model, the underlying information space, to actually make decisions, to actually then iterate again through your ConOps or your mission effectiveness. And so that is effectively what we've done. When we first started, this was characterized as the problem. Again, it was that there was a lot of stovepipe analysis being done, and different individuals would actually take in requirements, produce a report, hand it to the next person, and around. And so it wasn't tied together very well at all. And so what do I mean about cross-domain analysis? Well, I have two examples. One is that, if I have this mission that needs to do continuous surveillance, and I have a UAV that needs to be refueled to actually do that surveillance. So I really have the mission, which is actually two different air vehicles working together. And the connection point is this valve right here. Well, this valve effectively is in the mechanical domain. The switch that controls it, opening and closing it, is in the electrical domain, which actually needs to be connected from a communications point of view to the remote operator that's controlling it. But then I also have an independent domain, such as fire control. And so cross-domain is all these kinds of things. And notice that it actually goes across at the actual system or subsystem level, but it all goes all the way back up to having an effect on the particular mission in terms of how long I can actually spend out there doing my surveillance. Another example that's related more towards what we've been doing, but it's mission level optimization, came out of Brian Chell's dissertation, who was on our team for a while, is that there's these various different kind of mission level decision variables that we're needing to consider. And we actually have these combinations of, physics kinds of things. And in terms of like the catapult or other kinds of ammunition that is fired, we actually have to deal with exterior ballistics, what's happening as it's moving through space, the environmental kinds of things, terminal ballistic, what happens when it hits, and then factoring that around to actually ideally optimize our mission level parameters. And that is effectively what we've been trying to do. So in terms of like our digital engineering roadmap, I think we've been tracking. So just to put together the things that you're going to hear about are the combinations of how we've used model-based systems engineering to strengthen systems engineering, how it's going to be supporting decision-making, and we actually use what's called ontologies, which is in some ways the taxonomic representation of that kind of information. I'll hit on that in a minute. We also have used semantic technologies, things that are actually go along with the language of ontologies, plus all the query mechanisms and automated reasoning kinds of things that go into effect, including the different kinds of repos that are affecting it, so that we actually have greater semantic integration across the domains. And with that, we've actually created, again, a way to actually have an authoritative source of truth that's actually linked together through this interoperability framework. We've basically created a number of dashboards, which I'll actually show two, one on digital thread that and another one that's really based on a decision framework of that trade space analysis. And then what we've done is also gone beyond processes to actually describing the particular methods, which are the artifacts that should actually be produced along the way. With that, it's basically becoming an enabler for AI, because once we have these graph representations, which is what we actually store in these repos, we're basically going to be able to enable that with machine learning and AI. And we've also actually shown how we can do that in a different task that we had done. It was WRT 1025, where we looked at the combination of machine learning and artificial intelligence to support digital twin architectural patterns. So then where are we? Okay, so now what we've been able to do is we've been able to pull these kinds of things together, and we have this system, this underlying system model that's represented that gives us, consistent syntax, the ability to have, different kind of coordinated simulations in terms of digital visualization, so that the systems engineer can actually leverage reasoning and optimization and analysis of trade space, and then actually raise that level up to the decision makers. And that's what we've tried to do. So we really want to go from a lot of the decision makers, they want to see this from the beginning and say, well, geez, I really like the solution over here. But it's going to take too long to get it. What's my trade? What do I need to change possibly? And so with our digital thread that you're going to see at the end, you're going to be able to see that, well, I can see all the variables that I might want to change, and then I can rerun them through these workflows continuously as I actually change my decisions. So this is what we've called the full stack of models. This is one of the original distro A slides that was approved for use. And so when I talk about the full stack, we in some ways have reference architectures, and those reference architectures actually map very nicely to our ontologies. And then we have mission models that are actually hooked together with graphical ConOps. We use graphical ConOps in a various number of ways. One is to actually, in some ways, validate what we're trying to do, but also use it as a integration mechanism, so that we've actually linked together 1D, 2D, 3D kinds of things, and actually feed the information back to the either mission measures or system types of measures. We have our system of analysis, which is what we've created is we've done that in a SysML, which is an MBSA oriented kind of an approach that actually describes the system analysis. So it actually talks about the various kinds of tools that would need to be hooked together in a workflow, such as computational fluid dynamics, which is how the air flies over particular things. In addition to, what structurally does that need to look like, say, using, say, finite element analysis, to like how does it actually fly, 6 degree of freedom kind of flight. And then we've also demonstrated, and we use more of this this is the OpenMB, has a automatic generation of the actual models directly from information, and then we've applied digital sign-offs, which again, I'll talk about that more in the next task. So how do we do that? Well, this is the workflow. So we first start a repository, which is referred to as a triple store. It basically is the way that we hold information. It's subject, predicate, object, and then we would fire up our interoperability framework and load the appropriate ontologies that are related to a particular domain. The example that we have here, we typically always pull from SysML models. We use the Cameo tools, or now it's CATIA, but it actually describes not only our mission or system models, but also describes the system of analysis, which is used to automatically configure our ILAF, and I'll actually give additional details for workflows such as things that might be using geometric models using Creo or MATLAB simulation and or other kinds of things that are our dashboards, and they run in, say, for example, in Python. All right, so what is the workflow that I'm going to actually show a little bit about here today? It's one that we have our Catapult. So we have our system model. We have some analysis for how it actually is initially sent off, launched. It might have an error of, the height or the actual direction, to fire simulations to actually see where it's going to go, and then to actually error calculation at the end, all based on whatever the particular geometries are. With those things, and so that things of real interest are these measures of effectiveness, such as the impact angle, range, flight time, how close does it actually hit to the target? So those are the things that we want to actually take the low level analysis in the workflows and be able to map those things to those higher level kinds of things. And how did we do that? Well, what we had done is we formalized a methodology or a process that was created by Dr. Matt Chili, who used to work for the Armament Center. And what he had done for his dissertation is he actually said, what we really are interested in these actual mission objectives. And then what we need to know is what are the parameters that are necessary to actually map through various kinds of simulations to those objectives. And then when you do that, then you can actually have a trade space plot of the information to actually show, lifecycle cost versus performance versus how long is it going to take to get it versus long-time viability. And so these are the things that decision makers want to see. And so we've figured out how to actually automatically configure our mechanisms for interoperability with that. And the way we have done that is that we create a representation. So this was referred to as the assessment flow diagram. Again, it has the objectives, it has the simulation of the various parameters that are needed. So what we did is we characterized this in a parametric diagram that we refer to as the assessment flow diagram. So it has SysML is in the yellow here. So these are value properties. So that is that if you have a block, say, a UAV block, it might have a cruise speed of, say, 170 knots. That's a value property. So we describe all the different parameters that are needed. And then we also look at the various different kinds of workflows that might be necessary. And I sort of showed you the workflow. So we know that it actually needs to go through the error analysis that actually factors in the Creo models, then goes to the fire simulation that actually has a final fire error analysis that goes into the actual parameters, the metadata that's actually representing the value properties associated with the domain, so that people can actually do the visualization. So in just notional here, if it's yellow, it's a SysML model. If it's in this blue color here, that means it's these external simulations that we're actually using. So how do we actually map that into an ontological space? The way we've done it is that, so here are basically the blocks for the model, the Catapult mission, its system. These are what we refer to as value properties. And what we do is that we created a profile that has a thing called stereotypes in there. And these stereotypes are used to tag these various kind of blocks to say what they map to the ontological classes that exist. And that's how we actually understand what's going on. And so what gets pulled in then actually gets mapped from the SysML model to the to ontology aligned data. And that's across the various domains, as you just saw there. So from a big picture point of view, what is the generalization that I just actually explained there? So we end up having mission, system, subsystem analysis, and the system of analysis. It has its various different kind of value properties that could actually be mapped into one or more simulations that could be of these various kind of types. So we've made 5 of these different kind of workflows. So that information is actually seeds the particular parameters that go in. The simulation could run and actually map to, say, like a mission measure that would be associated with, like, again, measures of effectiveness. But some of the outputs of that data is actually metadata that's produced and stored again in other value properties that might actually be used by other simulations or other visualizations. And so we've also created yet a number of different visualizations. So we've done this where we've actually fed the information into dashboards. We've used it for our graphical ConOps. So in other words, we can actually say fly a mission and actually load the parameters that come about so that some person that's an expert can actually visualize it from a calibration and understanding point of view. So we're really using dynamic ConOps to actually understand requirements, but also validation of those kinds of things. We have an AR, augmented reality, and VR effort that's going on to actually extend that. That's related to the ConOps, decision framework, and a digital threat impact analysis, which is what I'm going to show. So effectively what you have is here is, in some ways, is the digital threat. The other thing that we've done is that we can make this work across different kinds of things. It doesn't have to be, it's not file-based. It can actually work on various different kinds of workflows, different kind of clients. So in other words, the various different engineers that might be involved in actually supporting these workflows can actually coordinate together, because it's all done through what's called a REST service, which is a way for us to do it in a very distributed way, which is really what you need for digital engineering. So here is a variant of one of our dashboards, and it actually shows that there's these different nodes that are actually the parameters out there, and you can see that they're linked together either from a requirement point of view, or if it's a part of something, or if it's an output to something that goes to as an input to something else. So this is the notion of how it works. What we can do is we can select any one or more parameters that are associated with it. And then what happens is that you can actually understand the digital thread by understanding the blue variables, which is the upstream and change parameters, and the red parameters, which are the downstream kinds of things. And then we have another tab, which we can actually like change values and push it back if we want. I'm not going to show that right now. But then the other dashboard that we created, which is really a rendering of the thing that Dr. Chili created a while ago, is that we can actually plot, and there's an underlying ontology that's for doing decision making. That's, again, not talked about in this particular talk at all, but in some ways we were able to like render those various different trades that we actually have, and then look at various different kinds of things that we can change, the objectives or value functions. And so we've very much been able to automate a lot of the decision making that's actually coming directly. So in other words, that information is actually in the repository. It's being pulled out in real time to actually render these particular dashboards. So it's continuously being changed and updated. All right, so how well have we done? Again, so we have actually developed 5 case studies with different ontologies, and we've been really evolving that methodology. I mean, it is continuously being updated because we are learning. This is still research, and we haven't seen very many things that have actually been done this way. And so the methodology in some ways formalizes the notion of starting with the mission and system objectives, and then determining those parameters that are necessary to actually populate the assessment flow diagram that was based on this integrated systems and engineering decision method that Dr. Chili created. We basically show and discuss how to actually tag these mission and system models with these stereotypes that are aligned to the ontology. So a lot of people say, well, I don't have very many ontologists, well, that's another point about why we used SysML. Is because a lot more people are going to actually understand how to make or read SysML, and then there's building an ontology it is definitely something that actually takes a lot of time. Our lead ontologist, Dr. Tom Hagedorn, has actually helped a lot of our team members understand it as we've been doing this for a number of years. And so then we've been able to show how we can use IOIF to actually use the AFD representation, that assessment flow diagram, to actually interconnect the models in simulation. So when it actually starts out, it actually reads in the AFD, it is actually configuring itself. So it's doing it based on the information in the SysML model. And so then what we use is Python code. We use a lot of Jupyter notebooks. They're really good for training, and they're good for a lot of different kinds of development, so that we can actually have these coordinated workflows for various different kinds of simulation and visualizations of the digital twin. And so also how well? Well, again, we are on our 2nd training course. We're also have a digital engineering boot camp that we're given to the Space Force. I'll talk about that in the next talk. And but actually, we're transitioning this to the Army, and the Army has permitted us to actually use this particular course that we have here with other of DoD kind of members. And we also have 2 PhD students that are actually investigating other use of the interoperability and integration framework. And so, oops, let me go back here. So yes, so we've had a lot of team members, and I just want to throw this out there. It's in there. I mean, again, we started with NAVAIR back in 2013, but it's like we've actually had, we started with the Army in 2016. Here are all of our people that have actually supported all these efforts. So this has definitely been a team sport. And with that, I will break for questions, but I wanted to open it up to Dr. Cook or Alan Gaska to actually make some comments if they would like first.
Hey, Mark, it's Alan.
Hey,
Can you hear me?
Yes, I can.
Great. Good morning, everybody. So Alan Lagaska, I am the primary technical POC here at the U.S. Army Armament Center. So I've been working with Dr. Blackburn and his team now for, well, I guess about 6-7 years. And there's been a lot of progress with regards to the technology, specifically the IOIF, the Interoperability and Integration Framework. It's gotten to a point where the technology has become a potential solution for us as a digital engineering ecosystem. There's still that challenge of taking that technology from the research and really putting it into a production environment. So there are still some things that we need to work out with Dr. Blackburn and his team, but it's certainly a potential solution that we're evaluating for our DE solutions. And with that, Dr. Blackburn has indicated that there is some willingness on our part to share the information. We're looking for other partners that might be interested in helping us take the technology to that next level of maturity where we can actually install it and use it in a government environment and use it for actual projects and actual project data. So I'll stop there, and hopefully Dr. Cook is also there. And if Dr. Cook wants to say anything, the floor is his.
Dr. Cook. Yeah.
Yeah. Hi, Alan and Mark. Thanks. I guess the thing I would add in kind of in our experience in digital engineering is that there's a lot of PowerPoint slides on digital engineering and a lot of proposals and marketing and discussions on, and most everybody starts with a slide with either arrows or lines connecting things. And I think what you see here is different in that those arrows and lines represent a specific property, a specific value, a specific element of information. So, when we look at options, a lot of the off-the-shelf, you can go buy it today stuff have lines, but they don't necessarily represent the integration that is necessary to do something. What do I mean by that? You can typically get two things to talk to each other, and you can view, for example, a CAD model from one vendor in another vendor's environment. But you might not get the parametrics associated with it to be able to edit that CAD model or to be able to do an analysis of that CAD model for structural integrity or whatever it may be. So I think this slide kind of shows the value of this approach, and why we think that it has potential is because it's specifically looking at sharing the information needed from one analysis tool or one analysis type to another, whether that's a parameter, a dimensional parameter, a stress, a material property, and sharing dissimilar types of things too between dissimilar types of models. So I think that's really what we're learning is integration of tools is not a binary thing. It's integrated or it's not integrated. What is the integration and what information can be shared across them, and how does that relate to the kinds of things you want to do with this ecosystem when and if you have it. And the other aspect is the ability to grow that thing over time and not get locked into something that can't evolve with you, because right now you've got a set of models that you use and that might represent a set of software in your stack, but that's not what you're going to have tomorrow or the day after that. So again, appreciate all the work and the progress. And as Alan mentioned, we're not looking to keep this proprietary to us in the Army. We're not looking to kind of be the ones that reveal the great solution at the end. We're trying to find 10,000 ways not to do it in order to find the one way to do it. And, the more we can exercise it, the better in that regard. Thank you.
Okay. Thanks, Dr. Cook. So I think that we have 3 at least minutes, I think, for audience questions. Is that right, Nicole?
Yeah, so we are starting the audience questions now.
NAVAIR.
Hey.
Hey, so obviously Dr. Blackburn and I have worked together at NAVAIR for a while. So I heard now it's Army and Space Force, and Alan said looking for partners. So let's swing this back around and let's get back engaged. And so, like, whatever work Mark has done over the years, and since his contract ran out with us, I'd like to take this back to my leadership and evolve it. And then I'm interested in the training classes that you guys have. So I want to follow up with that as well, because we're looking at, obviously, trainings that we can share and leverage. So
yeah, I'll talk a little bit about that. I have the slide on the set of training for the Space Force and the next next talk.
Very interested. Thank you.
You're welcome.
Do we have any additional questions? Jeff, yep.
Hello, Jeff Kerr from Virginia Tech National Security Institute. I want to ask a question that you and I were discussing yesterday. How well do you see this scaling into other domains, into the software development area, to the electrical design, RF spectrum? Have you guys investigated that at all?
We have done a little bit, I suppose, in the electrical area with this, but I think that it's completely scalable. In some ways, if you actually can characterize it like this in this particular picture, and I didn't go into a lot of the different kinds of things, but I think we can just do all that kind of analysis. I mean, I don't know if Jason or Alan want to actually chime in on what they think, because I know they were probably skeptical in the beginning. So.
Yeah, Mark, I guess not being a computer scientist and understanding all of the processing and memory implications of scalability, but just theoretically, if you could describe something with an input and output, and you describe what that input is, and that input's an output from somewhere else or vice versa, then it's plug and saga kind of thing. I kind of think about it as and I kind of think of that middle blue cylinder as the publish and subscribe broker of all the things, right? So if there's a diameter or a length in a CAD model that a FEA model needs, or a ballistic model needs, or whatever, it knows that parameter is the same thing, right? And it says, I'm going to take it from here and I'm going to give it to here. And so in my mind, it's got the potential for integration of dissimilar things for that reason. All you need to do is define what that is and make sure you define it the same way in each place, and then now you can share it. And that's kind of what we think about in terms of integration, but of what, right? It's of those data elements that are used by multiple pieces. But it's nice that it also only has to be those data elements that are used by multiple pieces. You don't need to move the whole model if you don't need to move the whole model. You just need maybe center of gravity, length, weight, and that's it. Yep.
question from our virtual audience, which is, a lot of your work is based in SysML. What are the implications of SysML 2.0, and are you looking forward to what that means?
Well, I'm very looking forward to SysML 2.0. Yeah, we actually, we're going to be working on that. Alan basically has put that into scope, and the way our tests are laid out, it's like we absolutely can actually do that. And I look very, very much forward to it, because one of the things that actually you can do in SysML v2, because it actually has a formal syntax, is to be able to actually generate basically more information related to, say, what are in the requirements. So in other words, if you have the UAV shall do this, we've actually got some natural language processing going on where we can extract out the subjects and objects and variables that are related. And with SysML, we can actually take our NLP stuff that we've been doing and automatically create a lot of the actual SysML information via SysML, because you can actually describe it from a language base. So I'm very excited about SysML v2.
All right, Mark, thank you very much for your presentation.
All right.
We'll be taking a short break, reconvening with Mark's next talk at 11:35. So if you want to transition between sessions either here in DC or online, please go ahead and do that, and we'll restart in a couple minutes. Thank you.